the closed line integral of the closed curve C1 of p dx plus q dy is equal to line integral over negative C2 of p dx plus q dy. All right, we're getting there, all right? We're getting there. We're almost done here. Another 47 minutes and we'll be done with this problem. Okay, so I moved this one to the other side, right? Which should have made it negative. But then I changed the path's orientation, which changed it back to positive but reversed the path, right? So we need to now come up with a parametric representation of negative C2. And remember, C2 went clockwise, right? So negative C2 goes counterclockwise, which is perfect because that's the way I like to parametrize circles. So what is the parametric setup for C2? X is equal to some function of t, which is a cosine t, right? Y is equal to some function of t, a sine t. T goes from 0 to 2 pi. If this problem seems like you would never come up with this on your own, that's because you aren't supposed to have ever come up with this on your own. This is to show you how you can attack a problem that looks like there would be no reasonable way to get an answer. This is an attack that you could employ on it. Now, somebody did come up with this, all right? That's why mathematicians lose their minds, is because someone had to come up with a way of doing this. So I'm sure someone struggled for many, many years trying to figure out how to do this, do something like this. But now it's a tactic, it's a tool in the toolbox. Other mathematicians use it. And all right, we're still going here, aren't we? We're going to try and do this one right now. All right, so now it's time to plug everything in. We got integral. We're going from 0 to 2 pi. Now, what is p? P is that guy right there, right? But we got to replace our x's with a cosine t and our y's with a sine t. Okay, so it's going to be negative on top, negative what? Negative a sine t over x squared plus y squared. Ah, this one's not so bad. What's this squared plus this squared?
1.
Yeah, you're close. When we square those, it'll be a squared cosine squared t plus a squared sine squared t. And you can pull out the a squared and you'll get your 1. So the bottom should just be a squared, right? A squared. Okay, that's this right here. That's p. Now what's dx? Derivative of this with respect to t, right? So that's going to be negative a sine t. Now I'm supposed to do dt now. But since these are both going to have dt in it, I'm just going to continue. Plus, what's x over x squared plus y squared? So x is this one, right? So this is going to be a cosine t over x squared plus y squared. We already know that's a squared. And then I have to multiply that by dy. So derivative of y with respect to t is going to be a cosine t. And then all of that dt. And if we're lucky, this should all work out real nice. Let's see. Oh, negative times negative, right? Oh, wow. Okay, that's going to be a squared on top, right? A squared sine squared. The a squareds cancel. So I get a sine squared t there. Same thing here, a squared, or a times a squared over a squared, that cancels. You have cosine squared t, you're adding them. That's just 1. So this is just equal to 0 to pi of 1 dt. And if you work that out, it's just 2 pi. It's messy, huh? But it's cool because, like I said, we showed for an arbitrary path, as long as it enclosed the origin, no matter how you go, as long as the origin's in there, your answer is 2 pi. And later on, if anyone ever gets into classes like complex variables or complex analysis, where you're doing things using complex valued functions, you actually get these things called winding numbers, which has to do with how many times, this is what we call a pole, and you count how many times you go around the pole, and you multiply by 2 pi, and it's your winding number, is the count of rotations. Someone has already shown that for certain vector fields, you're going to get 2 pi every time, no matter what. So all you have to do is count how many times you go around. So it does peek its head up later. Whew, all right, I like that problem. And we're at the end. How are we doing here? Yes? Do I need to leave anything up here or no? Okay, go ahead. Mm-hmm.
Has to be the opposite of C1.
And in order for us to, remember how I broke it down like J, K, and all that? And I was counting on those 2 paths canceling each other? The orientation of C1 and C2 had to be opposite directions.
Right. Mm-hmm. So does that orientation for C2 affect the integral that we just calculated?
Well, we did negative C2. Right? When I changed it, when we had this, if I'm gonna kind of summarize, we found that this that was 0. But because of the way we drew it, here was our arbitrary path C1 that way. I drew my little circle with radius A in here, called that C2. Because of that thing that I did previously where I went back, this way and that way, I know that this right here is the line integral over C1 of P dx plus Q dy plus the line integral over C2 of P dx plus Q dy, right? But that must be 0. And then I move this to the other side. And when I move that to the other side, my equals is here now. But they're not equal because this is now negative here, because I moved it to the other side. But then I got rid of the negative and made that a negative path, which now, computationally, I need to be looking at this path instead. Like computationally, to figure out this line integral, I just need to figure out that path that used to be like this, the other way, which is why when I used A cosine t, A sine t for x and y, if I let t be 0 and go to 2 pi, I draw it counterclockwise. I'm not sure if I'm answering your question.
Oh, yeah.
You sure? If I would have originally drawn my circle, like that, right?
Yeah.
Then, like if I would have started the problem, I said, look, here, someone give me C1, positive orientation. I'm going to come in with this little circle, and I'm going to do it positive orientation also. I could not have gone from here to here, right? So I drew it backwards so that I could go from here to here. And then, because it's 0, if this wasn't 0, we're dead in the water, okay? Because it's 0, then I can move it to the other side. All right. So the next mini exam, does anyone have the next one with them by chance? Can I take a look at it real quick? I just want to see where it ends. Six? I think we've turned in 4. We've turned in 5? Okay, 5 today. Area of a curtain. Okay, you can do that. Mass of a wire, center of mass of a wire. Going to need the textbook for that formula. Work done. Okay. Find a potential function, calculate a line integral. You can do that. Yeah. You can do the whole thing as of today already. The next one can be done. But it's not due till, what, next Wednesday? But remember I said there's like How many do the following after that? Two? Yeah, so if you're wanting to try and get that, your grade up, you probably want to just get that one done this weekend. Let's see, we have 2 days next week. We have 3 days left, right? 3 days left, and we have the hardest sections are 3-6, 3-7. We'll need all of next week for 3-6 and 3-7. That'll leave us 1 day. We'll probably need more than next week for 3-6 and 3-7. So maybe, yeah, let's just do this real quick. This right here, I think you'll appreciate. This is more computational. Here's a formula. Do it, and then we're done. It's not like you have to think, can I use Green's theorem here? Or, do I need to reverse the orientation? Like, this is very just, hey, we've got these new things, all right? And what I like about this is that it's very visual. I think it's very visual. I'm going to turn the light off because I want you to be able to see this. All right, so we have these two new operations called curl and divergence. And I'm sure some of you have already heard of these before. Curl, yes, no? Curl and divergence? Curl and divergence are vector field operations. So you need a vector field in order to talk about curl, and you need a vector field to talk about divergence. So if you're given a vector field F, we now define two new operations. The curl of F is one of them. When you calculate the curl of a vector field, your answer will be a vector. Okay, so if someone gives you a vector field, you calculate its curl, your answer is a vector. The divergence of a vector field is going to result in a scalar, which is basically a number. All right? So here they are. This is kind of like, remember when we did dot product and cross product of two vectors? If you take two vectors and you dot them, you get a number. If you take two vectors and you cross them, you get a vector. Well, now we're saying if you start with the vector field, you can do this thing called curl and divergence. One spits out a vector, the other spits out a scalar. So we're going to look at these one at a time. First, curl. All right, now curl, I know that looks bad. It's not as bad as it looks, all right? It really isn't. You can memorize the formula if you'd like, but I don't think you should memorize the formula. This is the better way to think of the curl. Now, we've seen this symbol, right? This symbol right here. This is what we use usually in front of little f to say find the gradient, right? But we're going to look at this as an operator, meaning I'm going to put this symbol here, okay, which is like the gradient symbol, right? Gradient. But then we're going to say we're going to take the gradient and cross it with f. So remember, when we say the gradient of little f, it means you take the partial of f with respect to x, right? And then y and then z, respectively. So this gradient means start taking partials. What we're going to do is we're going to take that gradient and we're going to cross it with our field. So you know how we've done cross products, right? We've done cross products many times. You have two vectors, 3, 2, 5, and we want to cross it with -1, 0, 2. Then we do this thing where we cover up, do the little determinant, cover up, do the determinant, change the sign, cover up, do the determinant thing. Yes? We want to do the exact same thing, but we want to do it with the partials and the vector field. So this is weird because this is not like this is an operation. So it's telling you, let me try and move that down, it's too high. If you want to find the curl of a vector field, what you do is you write down the partial with respect to x, partial with respect to y, partial with respect to z. That's your gradient, okay? You put that here, and then underneath it you put your field, PQR. And then you start doing your cross product. Okay, so you cover this up, and it's no longer this times this. What is it? It means take the partial with respect to y of r. Okay? That's the first piece. Then minus, not multiplication, this is an operation, the partial of z with respect to q. Here. Then you go and cover up the middle one and do the next one, change the sign. Next one, change the sign. And that's your curl. We'll talk about what it means, what the answer represents visually, geometrically, but let's at least do one problem where we just practice it, okay? We just do it. So let's find the curl of this vector field and then talk about the curl at a specific point within the vector field. So we want to find the curl of f, which we will look at as being the gradient cross the vector field, which will be, we'll write down partial with respect to x, partial with respect to y, partial with respect to z. I should have given myself more room. Give myself a little bit more room. Partial with respect to x, partial with respect to y, partial with respect to z. Then underneath it goes the field, PQR. So x squared yz, xy squared z, and xyz squared. All right, and then I'm going to do the cross product of those. So we're looking at these as like they're two vectors, and we're doing like a cross product. And our answer is going to be a vector. All right, so first part, cover this one up. What's this first one? What does this give you?
xz squared.
Xz squared. So you're taking the partial with respect to y of that, which is xz squared, minus, now you do these, so partial with respect to z of this, which is just xy squared. And now let's do the middle one. So we cover this one up. And how have y'all been doing this? Are you still doing like here to here minus here to here and then changing the sign? Or are y'all doing like here to here minus here to here? That's the way I like to do it, but when I'm first teaching it, yeah. However you do it, you need to do it, okay? So I'm going to have x squared y minus y z squared. X squared y minus yz squared. Okay, however you get that middle one, get it, all right? Then here, what's that going to be? Y squared z minus x squared z. There it is. There is the curl of your vector function. Or sorry, the curl of your vector field. Now, at a specific point, the curl of our field at the point 2, 1, 0 would mean just plug 2, 1, 0 in there for x, y, and z. So 2, 1, 0. So what happens if I plug in 2? X is 2, y is 1, and z is 0 for this.
First one
0, and then here, that should be minus 2, right? So the first one's negative 2, first component. Second component, x squared y, should just be 4 minus nothing, because z is 0. And the last one is 0. Okay. What the hell does that vector have in? You know, what is this, right? Like, what is this? What is this vector? What is it? How is it related to our field? I mean, obviously, this is has something to do with our vector field, right? But what is it? So now I'm going to try and explain to you what the curl of a vector field is. But this is just the mechanical process for it, all right? I know y'all are tired. I know you want to go home. But I'm really trying to lessen the pain of next week for you and me by giving us a little more time, all right? Well, let's talk about this one before we do it. What's the problem with this question? Find the curl of this vector field. The vector field's two-dimensional, right? And to do a cross product, we need three components. So we talked about this in the beginning. We just extend this field out, right? This field, we can change it to be 0, negative x squared, 0. And now it's in three-dimensional space, and so you can do the cross product with the partials. I'm not going to do it. This is just to point out that everything we do with three-dimensional vector fields, you can do with two-dimensional vector fields in terms of curl. All right? You're just saying, you're so eager, you want to know what it is, right? What's the curl? All right, so imagine, if you will, that we've got in three-dimensional space maybe water flowing down like through a river, okay? So at every point within the river, these molecules of water are moving around, right? Molecules are spinning, rubbing up against one another, right? So imagine you're a molecule moving through this three-dimensional space, and as you're moving, the flow of the water is pushing you in a certain direction, right? So you're wanting to go this way maybe. That's the vector field. The vector field is telling you the direction and the speed at which you are trying to go. That's the original vector field. There it is, right? At every point there's a vector. The curl has to do with, are you as like a molecule, are you rotating, are you twisting, are you curling, are you turning as you're going in that direction? All right, so almost like a little planet moving through the universe. Yes, it's moving in that direction, but is it like rotating as it moves? And that's your curl. So I have a visual, it's not the best, but here it is. Okay, so I got to make sure I get this right. All right, yes, okay. So let's say we are sitting here at a point, right? That's our point right there. That's a little molecule. We are within a vector field, all right? So there's a vector field. The red vector is representative of the vector field. It's telling you the direction you're wanting to go, all right? So we want to move in this direction of the red vector. However, the green vector is our curl. So now what I'm going to do is I'm going to start a clock. Okay, so do y'all see this little, like, I made this like circle with a little line on it. Do y'all see that? I mean, obviously you see it, but can you, relatively speaking, can you tell that disk is perpendicular to the green vector? So the green vector, what it does is it gives you an axis of rotation for your molecule. So again, we're moving through here, right? We want to go in that direction, but as we move that way, we're spinning, and maybe this is your axis of rotation like this. So as you're moving that direction, you're wanting to rotate around that axis, all right? So the curl vector gives you an axis of rotation, and what do you think the length of the curl vector tells you? How fast you're rotating, okay? So the longer the vector, the faster the rotation is. So what I'm going to do right now I have the computer calculating my curl vector, which is the green one, and then I have my computer calculating the length of the curl vector, which right now is 1.799. And I want you to notice how fast this wheel is turning. So at that point, if you were a molecule, you're moving in the direction of the red, but you're rotating on an axis of rotation with the green, and you're rotating, well, I guess pretty fast. I don't know. Let's move somewhere else in the field, and let's see what happens. So I'm going to pause it because I might cause some issues here. No, this is way too big. Still too big. Move us around. trying to get a smaller curl. There we go. We have a smaller curl there. So I've moved myself into a different part of three-dimensional space here. Try and spin this around. Well, that's pretty good right there, right? And now let's act like there's time. See how much slower that is, right? Now I believe when I wrote the code for this little animation, I made the green vector always the same length. That way you could see it, because I think I was making where you'd move it around, the green vector would get so small you couldn't see it, or so big you couldn't. So I just made it almost like a unit vector. But the clock here, this thing that's showing you how fast or how long it takes to go around, that's, I guess, the more important thing. All right? Does that make sense geometrically? Okay, that's your curl. Now, I need to go back and stop that one. What about in two-dimensional space? What's curl in two-dimensional space? It's the same idea, okay? But in two-dimensional space, it's almost easier to visualize because you can imagine that you're a point, and that point is in some flow of water, let's say, but it's like a flat sheet of water. And you can tell here the flow on the outside, right, is more than the flow on the inside here. So it's almost like you're a little molecule going down, and it's like you got these little paddles out the side. If the flow on this side is stronger, it's going to push these paddles harder than this, right? So if I start moving this thing, let me move my X. If I start moving this to this side, then I start to get my curl, because these are pushing more than these are. So here my curl is in the clockwise direction, right? And that means my curl is, this is actually the magnitude. Wait, magnitude, hold on. Where am I getting that negative from? Oh, the negative is from the right-hand rule, the direction in which if it's going in or out of the paper. So I put negative there because we're turning clockwise. If I move myself to the other side, right, then we're going to have counterclockwise rotation. And if I was right in the middle, I think it's right there, I should have like, well, I have a tiny bit of curl there, right? Because I'm not quite in the center. I'm just barely turning. Can you all see it turning a little bit? Yeah. So now we can change the vector field and different things are going to happen. So here's a different vector field. And if I move around in this vector field, look at my curl. Is it changing?
No.
Curl seems to always be 0, doesn't it? Yeah. I wonder if, like, if a vector field has the property that the curl is always 0 everywhere you go, if that's any sort of special type of vector field. Here's another one. Here's another vector field. This one, the curl is not always 0, is it? Oh, it was 0 there. Oh, pretty close, right? But if I move it this way, I've got some curl here, right? So I'm wondering, yeah, I wonder if you have a vector field where everywhere you go the curl is 0, I wonder if that's special. So the curl of a vector field creates an axis of rotation, and the magnitude of the curl gives us a speed of rotation about a point. If the vector field represents the velocity field of a flowing fluid, then the curl measures the tendency of the fluid to rotate or curl at given points in the fluid. If the curl of a vector field is 0, then there is no rotation, and the field is called irrotational. So if you go to a certain point in the vector field and you have 0 curl, then at that point it's called irrotational. All right? My question was, what if you've got no rotation everywhere in the field? I wonder if that's special. This just says that we can always extend two-dimensional vector fields into three-dimensional vector fields. What? Suppose F is a vector field in three-dimensional space. And suppose that the curl is always 0. Then your field is conservative. That's the property of a conservative vector field, is that everywhere in it you don't have rotation. That's what makes conservative conservative. All right? So that's what this is saying. If your curl is 0 always, then you're looking at a conservative vector field. And this is now the check. For, we started earlier and we're like, hey, what if we have a vector field in 2-dimensional space? We had a quick check for it, right? But if it was in 3-dimensional space, we didn't have a quick check for it. This is our quick check for 3-dimensional vector fields. Calculate the curl. If you get the 0 vector, you are looking at a conservative vector field. Now, why is it? Let's see if we can make sense out of why this is true. Let's see. Maybe I can convince you of why this worked earlier. What if I have a vector field that's in 2-dimensional space? The check for it is this, right? This is the check for it. But if I use this instead, then I need to extend that out into 3-dimensional space, don't I? And then when I calculate the curl, cross the gradient with the curl, with the field, this will give us partial with respect to x, partial with respect to y, partial with respect to z, and then this will be p, q, and r, right? P, q, 0, thank you. I'm happy that you're still right there. That was awesome.
Well, I'm here as much as I possibly can.
No, it's great. That was a quick response that was nice.
Maximum effort.
Okay, so think about this for a second. 2-dimensional vector field, all your vectors are on a flat sheet, right? The curl vector should be orthogonal to that, right? Because your curl vector is supposed to give you an axis of rotation. So if you're talking about a flat sheet of paper, like all those vectors we just saw a second ago with that little wheel I had, right? That little wheel here. In 2-dimensional space, your curl vector should be coming out at us. Yeah. So if I give you a vector field in 2-dimensional space, we extend it to 3-dimensional space, the only part of this thing that matters is the z component. Because that's the part that comes out, right? So if you calculate this, I would need, in order to, if this is true, then in order for this thing to be conservative, I need the z component of this thing to be 0. So how do you get the z component after you do this cross product? You cover this up, right? And you do the partial of q, partial with respect to x of q minus the partial with respect to y of p, right? And you need, when you do that computation, that you get 0. Yeah. And that means they have to be equal to one another, which is where this comes from. So this actually comes from this right here. All right, it's not the other way around. It's not like you did this and now we do this. It's this first. All right, curl. Now, divergence. We're almost done. Divergence, I have good news, is much easier to calculate. Divergence is by far the easiest calculation in terms of these vector field operations. If somebody gives you a vector field, PQR, and you want to calculate this thing called the div of f, or the divergence of f, all you have to do, take the first one, do the partial with respect to x, plus second one, partial with respect to y, plus partial of r with respect to z. So all you're doing is partial x, y, z. It's almost like the gradient, but you're adding them together. Okay, and your answer is going to be a scalar. The notation here we use is div f, or the differential operator dotted with f. Let's do one. That's the same vector field we had a second ago, isn't it? Okay, so we calculated the curl of that. That took a little work. But the div of this, much easier. Div f equals partial of that one with respect to x, right? 2xyz, plus partial of that with respect to y, 2xyz, and finally last one plus 2xyz, which is 8xyz. Notice this is a scalar. 6, it is 6. 6xyz, right? So now at the point 2, 1, 0, what's our div at 2, 1, 0? 0. And that's not a vector. So this is the same vector field that we did the curl on. We said that when we did the curl at that point, we actually did have some curl, didn't we? And now we're saying at that point our div is 0 though. Our div is 0. So what's div, right? What's the div? What's the divergence of a vector field? How many of you are kind of familiar with what the curl of a vector field was before we came in? Yes? Any ideas or explanations as to what the div is? Have you ever had a good explanation of what div is?
Like when they don't meet.
When they don't meet, yeah, like they diverge, right? Okay, I'm going to do my best. I'm going to do my best to do this. I spent a lot of time writing the code for this animation, so let's see if, not recently, but a while back. Okay, so first we'll kind of define it. If the vector field represents the velocity field of flowing fluid, then divergence measures the tendency of the fluid to diverge or leave a point in the fluid. Given a point in the domain, if the div of f is greater than 0, the region is called a source. So if you get a positive number for your div, then we call that point a source. And I'll show you the animation, maybe it'll help you see why. If the div is calculated to be negative, then at that point, that little, the region around it is called a sink. And then if your div is ever 0 at a certain point, then the region around that point is called incompressible. All right, so curl had to do with twist. Div has to do with, I don't know, here, this is what it has to do with. All right, that is an infinitesimal point. This is an infinitesimal point that we have zoomed in on. So it almost looks like a little ball, right? Or you know what, better yet, imagine that there's a point in the center of this thing. And what I'm doing is I'm just going a little bit outside that point and creating this little ball. But I mean, we're talking this is like an infinitesimally small ball, all right? And what I'm doing is I'm going to every point along this ball, every point along that ball, and I'm looking at the vector field. So do you agree that at this point there's some vector, right? At the point in the center there's some vector that tells me the direction I'm going. The curl tells me about the twist. The div has to do with looking around the ball, around that point in a little infinitesimal ball, and looking at all of the vector field. So at every point there's a vector doing something at every point on this little ball. So I'm going to show you all those vectors now. Okay. All right. So imagine I have a ball here. All right. Imagine I have a ball here. And I pick a point on the edge of this ball. I might have a vector that's doing this, right? From the field. This is the field vector. It might be doing something like that, right? In this case, that vector would be coming out of the ball. But you could have, if you move over here, maybe the vector actually points this way and now is going into the ball and punching out the other side, yes? All the vectors you see in green are moving out of the ball. All the vectors you see in red are going into the ball. Does it look like you have more green or more red here?
More green.
You have more green. And that's why your divergence is a positive number here. You have more going out than going in.
And I'm guessing when there's more going in than going out, it's negative.
Then you're going to get negative. So what I'm going to do is I'm going to, first of all, I can shrink this ball down a little bit so that you can see we're really looking like infinitesimally small. You can still see there's like more green than red, right? So if I zoom out, don't let the zooming out freak you out. I can also move the ball out, like take the ball completely out of here. You just kind of know that all those vectors are on a ball. I can increase the number of points we're talking about on the ball. So like if I want to add a bunch, you can really convince yourself that the div is positive here, right? And we can zoom the ball. I haven't looked at it. Okay, so we can zoom in if you want, so you can really kind of see what's happening, right? Now let me move it around. Let me move the ball. What's happening here? Looks like you're starting to get more reds involved here. Look at your div up there, 0.8, 0.6, up, 0. So 0 does not mean that nothing's coming out, nothing's going in. They're balanced out. You have the same amount going in as is going out. But once you get to some critical point, you start going, oh wow, look at that. I mean, the red just overwhelming. There's more going into the ball than out. And they're going in, they're longer vectors, so it's almost like everything's, so it's like the region around the point, things are wanting to go into that point. So that's why they call it a sink when the div is negative. And then if it's all green around there, then if you're somewhere on that ball, the likelihood is that you want to go away. So you're a source. And if the div is 0, then they say it's incompressible because basically there's the same amount going in as out, so it's like it doesn't want to move, right? Just kind of wants to stay there. Incompressible. That's the div in 2 dimensions. Here's the div in, in 3 dimensions, that's the div. Here's the div in 2 dimensions. You can kind of see it same way. Here, we move to the side. Look at our div. 0, right? Can you all tell a little better on this one that when I'm talking about the vectors, I'm picking vectors on the edges of the circle. Some of them are going in, but these on this side appear to be going out, right? That was what was happening on that ball too. Now for this vector field, it looks like our div is always 0, doesn't it?
Yes.
It looks like it. And that would just mean that every point here is incompressible. We have no sources and no sinks. So I'll change the vector field. Okay, now we've got some div, right? We've got something going on, a little more interesting. Positive div, negative div, still negative. Yeah, get the idea? Okay. Don't worry about that. Don't worry about that. Don't worry about that. Done. Okay. We are at the end of 13.5, right? 13.4. So if I'm not mistaken, was that 5? Why does it say 13.4 at the top of that? Oh yeah, I closed. Oh, I did close it. Yeah, that's why. Frickin' idiot. I'm calling myself an idiot. Okay. Yep. Okay. So we have 3 sections left, and we have 3 days. That's great. What's that? 3 sections in 3 days. So we'll be good. I think. Is it 3? Wait, is it 4? Oh, 9. I forgot 9. But I tell you what, 13.9 is going to go so fast. It's a very fast section. All right, everyone. Get a good, have a good weekend. Come in ready on Monday for 13.6. All right. And do your homework. That's a good idea. Homework.